All right. Without further ado, welcome everyone to our new session of community interest meeting. This is a relatively new series in artificial intelligence and digital pathology, and we are we're so glad to be joined by two speakers, Dr. Annie Martel and Dr. April Khademi, today to discuss how to move forward with AI development in digital pathology and with a multidisciplinary approach. A little bit about this program. So my name is Lingxin Zhang. I work in Mount Sinai Hospital in University of Toronto, and along with my colleagues, Dr. Susan Zhang from UHN, Dr. Fang Lu from Sunnybrook, and Dr. Yanis Prasis from UHN, we are bringing a series of virtual community interest meeting on this new topic, and we really appreciate the great support from our CPD office, led by Dr. Annie Plotkin and Miss Jenny Bozek. So this effort is really mainly targeted towards the University of Toronto community and partnered by T-CAIREM. We are working together to better understand presence and future of artificial intelligence, and hopefully we'll bring resources and people of interest together in this new era where AI is playing a growing role in pathology practice. Well, like both our speakers are so well established, I have to, your titles and accomplishments can hardly fit on this page. First, we have Dr. Annie Martel, who is a professor in medical biophysics of University of Toronto. She's a senior scientist at Sunnybrook Research Institute and also affiliated with the Vector Institute and T-CAIREM. She is an active member of the medical image analysis community and a fellow of the MICCAI Society, which represents engineers and computer scientists working in this field. She has served as a board member of the MICCAI and is on the editorial board of the Journal of Medical Image Analysis. And she obtained her uh, um, uh, uh, degrees and did his education in medical physics in UK before she moved to Canada in 2003. Her research programs have focused on medical image and digital pathology analysis, particularly on applications of machine learning for segmentations, diagnosis, and prediction or prognosis. In 2006, she co-founded PathCore, a software company developing complete workflow solutions for digital pathology. Our other guest speaker, Dr. April Khademi, is a Canada Research Chair in AI for Medical Imaging and Associate Professor of Biomedical Engineering at Toronto Metropolitan University. Her lab, the Image Analysis and Medicine Lab, or IM Lab, focuses on the design, development, and deployment of AI algorithms for medical imaging. Her research is funded by the Canada Research Chairs Program, CIHR, ERC, Ontario Government, Alzheimer's Society, Canadian Cancer Society, and MITACs. April has affiliations with the Vector Institute, U of T's Medical Imaging and Institute of Medical Sciences, St. Michael's Hospital, Institute for Biomedical Engineering, Science and Technology, and T-CAIREM. She has a PhD in electrical engineering from the U of T and has previous research roles at University of Guelph, GE Healthcare, Omnix, PathCore, Sunnybrook's Research Institute, and Toronto Rehab Institute. She's a licensed professional engineer in Ontario and IEEE senior member. All right, that's really impressive. I'm really glad that both of you can join us and talk with our pathology friends. So we'll start with Dr. Annie Mattal, Dr. Annie Mattal's talk, and after her presentation, we'll have time 5 to 10 minutes for questions, specifically related to her presentation.
Okay, great. Well, thank you very much for the introduction. Can you hear me okay?
Yes, we can hear very well.
Great. So I thought for this talk, rather than trying to go into all the sort of hardcore AI methodology, I'd try and just give a broad sweep of some of the work that's being done on AI and digital pathology at Sunnybrook, just to give a kind of broad perspective of what we do and maybe open up the possibility of some collaborations with other folks doing the same sorts of things. So this was my disclosure. I co-founded PathCore. Okay, so our involvement in digital pathology at Sunnybrook went back a very long way. In actual fact, one of my colleagues, Dr. Martin Yaffe, and he's a medical physicist interested in mammography. And his original motivation was actually to try and correlate mammogram images with pathology images so that he could look at some of the underlying biological sort of mechanisms that created contrast in these images. So what he started to do was to try and generate whole mount images of the breast, which is a fairly difficult undertaking. It's like not very commonly done. So he had a graduate student, Gina Clark, work on a very sophisticated pipeline to embed whole mount mastectomy specimens and lumpectomy specimens. Involved things like kitting out a laboratory from scratch for things like meat slices from grocery stores and things like that. And you can see now that they're able to do whole mount images from things like pig hearts and whole prostates, whole brains even, and do all that within the lab. So I became involved because I didn't really have a good way of viewing all those images. So way back in about 2006 or so, in fact, even earlier than that, I found a research software developer, Dan Hossinzadeh, who was able to Dan came into my lab with the remit of developing a good quality viewer that couldn't just view these whole slide images, but could also then assist with research into that. So it would allow you to do sophisticated annotations, it would allow you to do side-to-side viewing and image registration and all sorts of things. So Dan built this lovely viewer called the Khademi viewer, which is actually still downloadable today from PathCore. And this kind of kickstarted my interest, because not only was I interested in the software to display these images and in co-registering it to MRI and mammography and things, but it became very, very interested in the beautiful images, actually. I mean, there's so much information in a digital pathology image. It's information at all different scales. As an imaging person used to MRI, pathology seemed like the ground truth. So if you could analyze a digital pathology image, you could go so much further. So that's when I started to look at different kinds of applications. And we started off with some fairly straightforward classification work, trying to triage areas of a whole slide image. But then I realized, well, it's really important not just to build tools, but build tools that are actually useful. So this slide here is called Defining the Task. This is part of a talk I gave up at Vaughan on how pathologists can play a part in AI and digital pathology. And really the key role of a pathologist, I think, in digital pathology research, or one of the key roles, is defining the task. So telling people who want to develop tools like me what kind of tasks are useful. And you can see from this slide, there's a whole ton of different tasks that you can do. You can do quality control, detection of disease, quantification, classification, segmentation, prediction, and so on. But we always need to ask the question, first of all, is the task amenable to AI? So which ones of these tasks can be done properly with AI? Do we have enough data available to train the AI algorithm? And most importantly is, what's the clinical impact likely to be? So there's no point me going off to develop a tool that can exquisitely segment single cells if that has no implication for an end task that a clinician is interested in. So fortunately, I was very lucky in that Sharon Nofek-Moses at Sunnybrook is a breast pathologist, and she was very keen on developing AI algorithms as well. So I went to ask Sharon, well, okay, Sharon, I've got these techniques. We were interested in breast cancer. What would be a really good application for AI in breast cancer in digital pathology? And she came up with this. She came up with a quantitative assessment of residual tumor burden. So breast cancer patients who have large tumors or certain kinds of tumors have neoadjuvant chemotherapy before they go for surgery. And we know from research done by Simons and others that if you can evaluate the residual cancer that's left after neoadjuvant chemotherapy, so you take the resection specimens and you look to see how much residual tumor is left, that's an important prognostic indicator for future therapies. And the standard of care is pathological complete response, as you all know probably. So have all of the tumor cells disappeared. But it turns out that if you can do a more sophisticated assessment, you can get a much better prediction of outcome in the long term. And this outcome assessment involves several different components. So the first thing that we have to do is find any residual tumor cells in the resection specimen, and then characterize how much of the tissue is covered by these residual tumor cells. So this is the tumor bed extent here. Once we know where the tumor cells are, we want to assess how many of them are there. Are they very dense? Are they very sparse? And so on. So this is the cellularity. We need to be able to distinguish between in situ and invasive, and we also need to be able to characterize lung metastases. And the reason why Sharon suggested this as a suitable task is because it takes a very long time. So although we know it's useful, it's very rarely done in clinical practice because it just doesn't fit in with the clinical workflow very well. And it has a lot of extra components above and beyond what's required by the college for reporting. So she did some timing on a bunch of these studies here, and you can see here the time spent in minutes to get a complete pathological response assessment based on this residual tumor burden assessment calculator. And you can see that in some cases, for example, a complicated mastectomy with residual cancer, there's over 46 slides in the box to go through. It took, in this particular case, 180 minutes because it was a complicated case, different areas of residual cancer, a lot of things to calculate. So this is what we started off with. So it obeyed all the rules. It's amenable to AI. It's solving a real need. And we had plenty of data that we could use to try it out on. So the first thing we did was we had a research fellow, pathology research fellow, Shireen Salama, under the supervision of Sharon. So they collected a whole bunch of whole slide images. This was done quite some time ago in 2018. And then Shireen went and dropped down these little 512 by 512 boxes. So she collected patches that had normal tissue. So the purples here are zero cellularity. And then she also collected other patches over different areas of the tumor and assessed how much residual tumor was left there. I'm just going to put a laser pointer on here if I can find one. Right, so you can see here, there's some little patches here, and each patch has got a continuous number from 0 to 100 on how much cellularity there is. And we actually made these patches available publicly, so we released this as part of an SPIE meeting challenge. So what you do with these challenges is you release a public training set. So we released over 2,500 patches from 37 patients, and they each had these values attached to them. And then the contestants go away, they try and train an AI model to actually carry out this task. And then we have a separate set, a test set, which we then release right at the end. And then they run their algorithm again, and they send us the results. And then we can assess them. And what we found was that this was very early in the days, and this is one of the first tasks for actually calculating a continuous variable. We found that all the teams did very well. So 317 teams registered, so lots of interest in this. Most of the teams use what is now considered to be fairly standard technology, a convolutional neural network. So you just feed the images into a convolutional network, it runs through the network, outputs the result, and then you see whether the result matches the input, and then you keep iterating around. So it's a fairly simple way of training. And the teams that entered had no experience with digital pathology. So what this shows you is that the technology for AI is such now that with enough data and a simple enough task, it's actually fairly straightforward to train something. So the teams that submitted the entries, 21 of these teams actually managed to meet the performance of 2 pathologists. So our ground truth was we had one pathologist label the patches, and then a second pathologist also label the patches, and we looked at the difference between them. So the idea was that if the AI algorithm had the same difference, then it was a well-performing algorithm. So these are the sort of top-ranked algorithms here, and this ICC is just a correlation between the pathologists who did it and the AI algorithm. You can see that they all did very well. There isn't much difference between them. But where we still need, so this is people who knew nothing about pathology, but where you kind of need pathologists in there is, although this algorithm performed okay, there were still limitations, and it took pathologists to kind of understand what those limitations were. So what we did was we looked at all the patches in the test set and looked to see which patches were always correctly classified and which patches were not always correctly classified. So here you can see the P is the pathologist's assessment of cellularity, and A is the average of these algorithms. So you can see here, this is a normal piece of breast tissue, a normal duct, and you can see that most of the algorithms correctly predicted that this had zero cellularity, no cancer cells in here. And this one here you can see is an area of cancer, and you can see most of the algorithms got very close to the 90% that the pathologist had allocated for this slide. But these ones here are all errors, basically, that were commonly made. So here, these are normal cells, but many of the algorithms actually incorrectly thought those were cancer cells. And I guess the reason is because these were quite densely packed compared to this more normal example here. Here, again, the algorithms grossly overestimated how many cancer cells were there, and I suspect that's because they were all mistaking these lymphocytes around here for cancer cells. And then you get some of the less common variants of cancer here, different kinds. So here the cytoplasm of the cells is quite expanded, but this is included in the cellularity measurement. And here the cells are very loosely packed. So the message we got from this challenge here was that, yes, you can get a long way without any domain knowledge, but if you're going to really fine tune those algorithms and get the best performance out of them, you need a very, very diverse training data set. So you need a large training data set with many, many different kinds of cancers in there, many different types of patients, many examples. But you also need to go back and have a look at the errors and see where they come in so that can help you refine your algorithms. So the outcome of this basically was that cellularity was one of the things we could measure. So one of the other things we went on to was looking at detecting metastases in lymph nodes. So lymph node metastases is a very important task in all areas of cancer. Clinicians need to know, are there metastases in the lymph nodes before they decide what subsequent therapy to give patients? But it's kind of a labor-intensive and not very exciting task for the pathologist. It's also something where the pathologist can easily get distracted and things like that. So there's a good case here for AI because it can help automate some of the things. And all the pathologist then has to do is look at the kind of AI algorithm, see what the output looks like, and assess whether it's correct or not. So it's a real big speed up of the process. And here we certainly had enough data. There was a very famous challenge called the Chameleon Challenge, where a group from the Netherlands had taken data from 377 patients and had meticulously annotated all of the metastases in these patients. So there was a large public training data set available. And this data set actually was responsible for kickstarting a lot of the interest from commercial groups like Google and Page AI and things like that. The availability of Chameleon helped them to start developing commercially viable products for something that was actually useful. The only trouble with Chameleon is all of these patients in this data set were treatment naive. So none of them had had neoadjuvant chemotherapy. And again, Sharon pointed out, well, that's great, but neoadjuvant chemotherapy changes the tissue. So this data isn't going to be very useful for us to train a detection algorithm for post-NAT things. So another research fellow, Dean Bathuni, came into our lab, and she did a wonderful job of annotating almost 1,000 slides for us at quite a high level of detail to show us where the cancer was, where the tumor bed was, and areas of things like extranodal extension and stuff like that. So we have a nice data set here. And then Tony Zhu, one of my graduate students, then proceeded to train an algorithm to try and detect these metastases. This was interesting, actually, because we took two different approaches for this. So the first part of training the algorithm was to take the annotated information and turn it into patches. So what you can see here on this image as it goes through is you can see these little square patches. So each square patch was given a label of whether it contained cancer or not. And we determined that from how the annotations overlapped with the square patches. He trained a patch-based algorithm, and this gave us, at the patch level, quite a high level of accuracy. And you can see it's a nice heat map here. So when you get to the heat map, you can see the darker the red it is, the more probable it is that that square contains cancer. And you can see the annotations are overlaid. So you can see we've got nice accuracy on this heat map, very, very accurate. But the problem with that is that you can see in almost all cases, you're going to end up with one or two false positive slides. So, for example, there's some area here with maybe 50% possibility of cancer and so on. So if you want to get an accurate probability at the slide level, you've got to somehow combine all of the patch information to give you a single number. So that's where an attention network comes in. It's a different AI algorithm. So Tony took a patch level network and then trained an attention level network on top of it. And he ended up with this really very, very accurate algorithm. We were able to test it on an internal data set that was the post-NAT one. We also took a couple of external data sets. One of them was from Memorial Sloan Kettering. This was a data set that was published by the group that went on to form Page AI. And basically what we're looking for here is a number close to 1. And our performance on our own data sets, and we've tested it on 2 different scanners. So one of the scanners was out of domain. If we set it to 100% sensitivity, so we set the threshold so that we're really, really sure we're going to catch every single metastases, we actually get a specificity of 70%, which is very, very high. And the reason why we get such a high specificity is we trained it on a very specific patch database. So because we had all the post-NAT patches as well as all the chameleon patches, it meant that we were able to get rid of all these false positive areas. So this is what happens when you train the algorithm on just data that has never seen neoadjuvant chemotherapy. You can see there's lots and lots of false positive areas appear in the heat map. It still finds the small micrometastases that's in here, but there's lots of false positives. So you can imagine as a pathologist, this isn't going to be a very useful heat map for you because you're not going to want to go through all of these different areas and look at it. If you take the patches that do have exposure to neoadjuvant chemotherapy, the algorithm has learned to ignore all these other changes. And you can see on this particular example here, we have a single patch that's come out as positive, and it happens to correspond to the metastasis. So this is very exciting for us. We're going to try and get this into clinical practice at some point. So you can see some of the examples here. This is a post-neoadjuvant example where this blue area here is the tumor bed. And again, you can see lots of false positives over the tumor bed. The advantage as well is we can not only get the tumor out, areas of tumor out now, but we can also get an area of tumor bed out as well to look at where those changes occur. And just for sanity's sake, this is the same model, but applied on a case which has got no neoadjuvant therapy. And you can see it does a very nice job of actually just finding the tumor there. Okay, so that was a diagnostic task. So in a way, this is the easiest kind of task to try and train. It's got definite clinical need. It's something that pathologists can determine whether it's working well or not, and it should have some kind of clinical impact. Somewhat harder to train a survival model. So survival models, what we're trying to do here is take an image, a digital pathology image, and decide how likely is this patient going to be to have a recurrence of that tumor later on, either a local recurrence or a distant recurrence. And are they going to have, is it just a recurrence, or are they actually going to have a death as a result of that recurrence? And there's 2 different approaches to this. One is the pathology-driven approach. So here we do things like try and recapitulate what pathologists have always done. So you've always got things like the Nottingham grade for breast cancer, Gleason grade for prostate cancer, and so on. These have been designed over the decades by pathologists who find imaging markers that they believe are related to survival, and they turn those into codified scores. And the nice thing about those is they're interpretable, they're more generalizable. A pathologist can look at an AI model output and actually say, okay, that looks correct to me. That's found Gleason grade 4 when it says it has, or yes, those are mitotic cells, and so on. And it's the advantage of training these models is that they can automate the time-consuming evaluation of features. So we can still use the existing Nottingham grade, but instead of having to do mitotic cell counting, the algorithm does it for you. The other way of going about it is data-driven. So here you have the potential to discover new biomarkers. So the idea with a data-driven method is you have images, you have survival times, and you just throw the whole lot into a big AI algorithm. And there are many, many different AI algorithms. They often use foundation models and so on. But the idea is you just go end to end. And the cool thing about these is they do have the potential to discover new biomarkers. So you may find that the algorithm is able to make a prediction, and if you do some other things to look at where it's paying attention to, so which patches are guiding that decision, you might discover some new biomarkers. You might learn something new about the underlying biology. These methods also scale very well with very large data sets. So the more data you give it, the more accurate they're likely to become. But on the other hand, there's a danger of overfitting on small data sets. And it's difficult to see when this model fails because you're not going to know for 5 years or so whether you were correct or not in your assessment. It's difficult to know if you say it's high risk, is it really high risk or not? So there's no real good feedback loop for knowing when the algorithm's not functioning as expected. So this was an example, sorry, I've gone these in the wrong order here. So this is an example of a challenge to try and reproduce the tumor infiltrating lymph, TIL score. So it's the tumor infiltrating lymphocytes in stroma score, in tumor stroma, that's used as a kind of biomarker. So there's a working group led by Sardego who's trying to say in breast cancer, if you have TILs that infiltrate the tumor-associated stroma, then that's connected to the risk of recurrence. So what the challenge did is it released a whole bunch of whole slides and a whole bunch of patches and cells. And then the task was to basically find the tumor and then estimate the TIL score over the whole slide image. So this is work by one of my graduate students. So he trained 2 different models. The first one found the tumor in the first place. And the second model was able to tell the difference between tumor-associated stroma and then counted the TILs as well. And he was able, using this method, to get a TIL score that was able to stratify between high-risk and low-risk patients. So this is from the challenge results. And then he used the same method and checked that it still worked on the TCGA data, which it does. The interesting thing about this work is that when you actually compare the sophisticated TIL scores with some of the clinical variables, you find that the clinical variables are actually just as good. So here's the TIL score here in terms of hazard ratio. But if you look at some of the other standard clinical features like the grading of the tumor, that actually does a lot better. Another example is a recent one for a digital pathology challenge on prostate. So here the task was to estimate time to biochemical recurrence. And many of the teams who took part in this competition had very sophisticated end-to-end data-driven pathways. So they took in the data, they had the final prediction of how long it took to recurrence, and they trained the model directly. Matthew McNeil in my lab took a different approach. He said, well, okay, let's just try and reproduce what the Gleason grade does. So what he did was he trained a model using some other data from a different data set. He was able to train a model that could locally detect whether it's Gleason grade 3, 4, or 5, generated a simple index, and then calculated a risk score based on that. And he actually found that his method won the challenge. And the reason why it won the challenge was because it performed very well on both the training set and out-of-domain test sets. So he trained it on some data from the Netherlands, and then it performed very well on this US trial-based data here as well. So the advantage was that it was interpretable, didn't overfit, and just worked very well. We're still doing a lot of work on these kind of highly sophisticated models. And if you're into survival modeling and digital pathology, you'll know that there's lots of interest in these big foundation models. So we've done some work where we've tried to predict survival on TCGA data using things like the Titan model, using state-of-the-art transmill techniques and graph-based techniques and things like that. So this is some recent work we've been trying to predict survival in breast cancer. But if you look at these C-indexes for overall survival here, the higher the better, you'll see that even these very sophisticated methods, which use a lot of AI technology, none of them have outperformed a simple clinical Cox model that's just based on cancer grade and staging. So we still have a long way to go, I think, in digital pathology for survival prediction before we can beat good old-fashioned pathologists. I'm going to skip over some work here. Foundation models are in the news a lot. We produced a foundation model way back in 2020, just using a convolutional neural network approach. I did this slide last September, so there are a bunch of very large foundation models here from Page, Microsoft, Harvard. This would have to be another 10 or so new foundation models. I updated it today. But the idea with foundation models is that it's becoming easier and easier to train large models because we can take pre-trained models from other data sets and apply them to new problems. So this is where a lot of the current work is going. And people are trying to train foundation models as well with language and things like that. I'm really going to have to blast through here because I'm almost at time. So I'm just going to blast through a couple of different things that we work on at Sunnybrook, just so you know some of the range of things we do. I actually do a lot of work with the biomarker imaging lab run by Martin Yaffe. So we have a multiplexed a multiplex system, fluorescence system here. So some of the work we've done is things like automatic segmentation of cells and cell boundaries and nuclei. And we've developed an algorithm that can be plugged into Cell Profiler, for example. I've done some work with some of the hematopathologists at Sunnybrook as well to try and quantify IHC staining, to look at the P53 staining. And we've shown that we're able to actually quite well predict whether there's a wild type TP53, whether there's a nonsense mutation or a missense mutation from under or overexpression of P53 in the IHC images. And we've also spent a lot of time developing some tools for pathology. So if you are interested in having someone do some work on digital pathology, a lot of the effort initially is sent in figuring out how to deal with these whole slide images. So we've developed a whole Python library that simplifies things like taking patches from the images. You can do different randomizations. You can take patches from inside annotations, patches from outside annotations, generate heat maps, and so on and so forth. So this library is publicly available. It's well documented. It's up to a good standard. I'm going to skip it. So there are a lot of places where pathologists have a real important role in AI. It's not just the domain of the computer science geeks. And the groups that are doing really well are those which are well integrated with good collaboration between both pathology and AI scientists. And that's because in all sorts of areas, we need that clinical information. So, for example, when you're collecting data, we need to know, is the data we're collecting to train our model representative? Does it show what we need to do for the disease? Is it from the right scanners that we're going to use in practice, and so on and so forth? We also need to know how to evaluate our algorithms. So what metrics actually matter to a clinician? Is it the sensitivity that we care about? Is it specificity? Does it matter if we can segment things, or is it just counting things that counts, and so on and so forth? How do we deploy it? So a lot of these models I've shown you, I haven't actually deployed in the clinic yet. And there are many different ways of deploying an AI algorithm in the clinic. And we really need the end users to say, well, I need this algorithm to do this. This is how I need to use it. And again, this is an area which we haven't done much of in AI yet as a group, but it's becoming more and more important. At the moment, this is generally being led by the manufacturers, but it'd be really cool if we could get a sort of critical mass together in Toronto to start actually testing some of the AI algorithms that we're all developing in a more clinically relevant context. And I think April is probably going to talk about that in the next talk. And then finally, evaluation of clinical utility. So all of these algorithms, we tend to test them in the lab, but really it's only with a human in the loop that we can really know whether this is actually going to improve accuracy or not. So we're never going to give a lymph node metastases result from an AI algorithm. It's always we're going to put it in front of a pathologist with the AI. So the question is, does it actually make them go faster, or does it make them go slower? Does it improve accuracy or not? And it's not obvious that it would make things more accurate. So this is a very important area. And we already so yeah, these are just basically to summarize some of the roles in AI development. So just to summarize, AI has huge potential to improve accuracy and turnaround time. We have to understand the data very well. We have to understand how to evaluate them. And we have to talk very closely to our end users. And that's right, it's not just pathologists as well. We probably need to talk very closely to surgeons and oncologists and so on and so forth. So finally, I just want to say thank you to all my group and to my clinical collaborators. In fact, this was a breast slide here, so I unfortunately skipped off my hematopathology collaborators. But I collaborate with many of the pathologists at Sunnybrook. So thank you very much.
Thank you, Dr. Martel. Due to our numbers of attendees, if you try to raise your hand, I can call on if you have any questions, but otherwise you're more than welcome to type your questions in the chat, and Jenny and I will like read off those questions. So we're still good in time. We have, about 3 more minutes before our next talk. We could also like collect all the questions towards the end. Well, we'll start with the more general discussions over Dr. Mattal and Dr. Khademi's work and how that's related to pathologists and how pathologists without, a substantial background of computer sciences coding can, have for these to understand their workflow. But maybe I'll start asking question, Annie. So you mentioned that, like you're using some pre-trained database data set, and I think there's a growing number of them, and there's a good publications. So how do you ensure the quality of it? So like, are they all kind of previously validated by pathologists or using the same standard? As you know, like even in breast pathology, some of the standards are kind of evolving over time. So,
Yeah, that's a really hard question. So something I'm actually actively looking into in the lab. So we have many pathology foundation models. So Harvard are doing it, Page AI are doing it, Microsoft are doing it. They all have their strengths and weaknesses. They all actually still have embedded within them some sort of bias towards the manufacturer. So none of them are completely free from the fact that if you put in data from one scanner and another scanner, it still captures the difference between the scanners and things. So none of them are perfect. And no one's really tested to see how well they perform against all downstream methods. So what we do typically is we take an AI foundation model and we try it out on several different tasks and see how well it does. So does it do well on a survival task? Does it do well on a segmentation task? And we try and pick one that does quite well across the board. But if we really are interested in one particular task, so for example, the lymph node metastases, I could take a foundation model on that and do what's called weakly labeled learning on it. I could just take the label of the slide and the image and try it. But in practice, if you have the annotations on your own data set and you have enough annotations, then that will give you quite good results. But if you do that, then it's less likely to go well when you try and move it to another center. So what these foundation models do is they increase the probability that when I train a model on Sunnybrook data, it will still work on UHN data. So that's the advantage of the foundation models. They've seen so much more data that the solutions you obtain are more likely to generalize somewhere else. But we don't know how to test them. We don't know whether it's better to have a foundation model that's only trained on breast for breast tasks or only trained on prostate for prostate tasks. And we tried to look at that in our 2022 paper and actually found conflicting numbers. So some tasks were better with a foundation model with many different cases, some with only a single case.
okay, thank you. So we have a question from the audience, Dr. Omar Mohammed. As a pathologist, especially from developing countries, can get to AI, is there a program, fellowships, courses, or research to help, pathologists get access? What are the requirements for beginning pathologists in AI? I think that's actually a general
Yeah, I
question.
think that might be best done at the end,
Yeah,
actually.
we can revisit that question.
Yeah, I
Okay,
think we should do
so
that
maybe
one.
we'll let April get our presentations and we'll start with a more group discussion. Okay.
All right. Thank you so much, Lingxin. All right. So I'm an associate professor of biomedical engineering at TMU, and I am the PI of the Image Analysis and Medicine Lab, or IM Lab. And what we do is extract insights from medical images using AI. And the problems that we focus on is using AI to generate computer generated biomarkers from images to augment workflows. So we don't build tools that are here to replace the pathologist. We build tools here to help pathologists do the job that they already do. So in the lab, we work on both radiology and pathology imaging. And so the kind of workflow considerations that we have is whether the tool will improve diagnostic accuracy, inter-rater agreement, turnaround time, and ultimately quality of care. So today I'm going to talk to you a little bit about my journey and the journey of digital pathology and AI for pathology. It's a little bit about how I've contributed or been involved along the way, but also some of the things that have happened in the society or in the field as a whole. So I started in this space in, I would say, 2012, and this was the first slide of my talk back then. So it says, just as radiology made the transition to digital over 20 years ago, pathology is undergoing the same transition. So that was about 13 years ago, and I would argue that this slide still applies. And so my talk will talk a little bit about this journey and kind of why we're still here. So my experience first started. I was hired. Actually, I was in the about to defend my final thesis. I have a PhD in electrical engineering from U of T, and I was kind of scouted by the company for GE Healthcare, and had to undergo several interviews from different levels, and what they had created was this innovation center, which was dedicated to digital pathology and innovation in digital pathology. And it was really one of GE Healthcare's or GE's first innovation centers in Canada. So it was really nice because we had the chance to do pure innovation that wasn't necessarily tied to money anyway, or right away at least. And so this is just us. We actually, this was one of the images that the GE Omnic scanner produced. It's a resection of a carotid artery. And actually, this is native resolution, actually downsampled. So if we would have, I believe it was something like 17 feet by 12 feet. So that is the native or close to native resolution of the images, just to give you a perspective of how big these images really are. So so I was hired there as algorithm development specialist. So I was there to try to understand how we can commercialize, how we can do R&D in this new field of digital pathology. But we were all kind of championing around how to integrate digital pathology into clinical care. So we now have a new piece of digital information, and we wanted to see how we can integrate this into both the patient and the information pathway. So some of the first kind of initial questions that we asked, we're thinking about is like, okay, now we're going to digitize the slides. How is this going to change the workflow for the pathologist? Because there is some change management required. And we did turnaround times, time and motion studies to really try to see how the pathologist interacts with the tools. We also looked at, what kind of APIs and different systems you need to integrate with the lists in order to automatically pull metadata needed for pathology reporting. We looked at, remote reviews and consults for telepathology. And my job was really there to look at how we can use computer-aided diagnostic algorithms to help detect and diagnose disease. And this was a very exciting role because one, I was getting trained in a new area. I had done radiology AI for all my studies and my degrees, but it was also very exciting because the company really was pumped about this. So we had a lot of support from the company as a whole to do innovation in this space, and it was right in an area that I did my PhD in. So it was great. So I sought out first trying to figure out if we wanted to create a new healthcare technology, how can computer-aided diagnostic tools actually help? And usually in any kind of new healthcare tech, we consider three things. Does it improve cost, access, or quality? So we could think about algorithms that speed up workflow or speed up pathologists. And actually, industry is very focused on that and how to make pathologists faster because they think that that's a nice ROI, nice return on investment. So you can go to a hospital and say, I'm going to get your pathologist to read 20% more cases, and therefore you could bill, for example, OHIP 20 with 20% more cases. And so this has been the main thing that industry has focused on for the last, I would say, decade. Was their big selling point. There's also algorithms that create access. So, for example, if you don't have pathology subspecialty in rural areas, such as like Timmins, for example, you could increase access to clinically relevant information. But as a scientist, I was most focused and cared most about algorithms that improve quality of care, because I think that's where we can have the biggest impact on humanity and the patients that we serve. So I took a dive into quality issues in pathology, and I was a little bit surprised to find some of these reports that actually few areas had pathology completely overhauled. And it was kind of a hot button issue at that time. And it was starting to be thought that maybe going digital could help with some of these issues of quality and pathology. And so I wrote a white paper on searching for new technologies to improve quality in pathology. And it started by looking at the different phases of pathology. So there's the pre-analytic that deals with sectioning, staining, etc. We have the post-analytic, which is reporting and follow-up. And then there's the analytic phase, which actually deals with the visual tissue analysis and interpretation. And so I started to look at the different scores and grading systems that pathologists use and to understand, what are the challenges with these grading and scoring systems. And so this article was in 2010. And what it is showing is the inter and intra observer agreement in breast cancer histological grade. And for a variety of cases and studies, we can see that there can be moderate or poor agreement in some of the grading tasks. And so I wondered why that was. And I tried to understand, first of all, really what are the grading systems. So I worked a lot with pathologists to understand how they do their job and what are the visual clues that they use for grading and scoring. And some of the things that I found that add subjectivity is, for example, selecting the correct high power field for scoring and grading. That could vary. There's also qualitative descriptors to explain visual cues. So, for example, pleomorphism. That's one that's kind of hard to really describe, like how pleomorphic a tumor nuclei is. There's also manual counting or visual estimating or of cells. It also is quite laborious. So then I sought out to design computer-aided diagnostic tools to combat subjectivity, reproducibility, and efficiency. And so back then, we actually only operated on patches. So we didn't have systems and abilities to process the whole slides yet. And typically, our software, which would analyze these images, were built from classical image processing tools such as segmentation, denoising, filtering, and all of the R&D was still done in MATLAB. Even the the other R&D scientists at GE Omnics, we did all of our pilot testing in MATLAB. But when we wanted to translate it into the viewer, we would use C# and C++. And so what is at the output of something like this? It could be, for example, a quantitative number. So like this is a simple example, maybe not super clinically relevant, but we've quickly counted the number of nuclei. But we can also offer visual guides on what we've been quantifying with an overlay. And in the beginning, industry was looking at IHC as the clinical use case for AI. It was called big data analytics back then. It was highly sought after by the industry in the early days because there was reimbursement in the US. So there was a CPT code that actually would allow for quantitative or semi-quantitative analysis. So what this means is that you could use an algorithm and use this code to get billed or to perform your billing. And I think it was something like $120 or $130. So companies were really excited by this, thinking, okay, you can use our quantitative algorithms and maybe we could charge you on a per click or a per slide model. And the funny thing is that it was FDA cleared. The algorithms to do quantitative analysis on IHC, this is for HER2 in particular, was cleared by FDA, but the scanning device to do clinical sign-out wasn't FDA approved. So you can see that the industry was already a little bit ahead of itself in that we could bill and we have FDA approved products for quantitative image analysis, but we actually don't have it, the scanner approved yet. So I embarked on research myself. I focused heavily on IHC and in particular Ki-67. And I was designing classical image analysis tools. And in this case, I didn't want to use the Beer-Lambert law, so I focused on a novel color separation method that basically estimates color vectors and does a color deconvolution. And what is the result? You get two channels, one with the hematoxylin positive and one with the the IHC positive and one for the IHC negative or the hematoxylin stained cells. And why is this important? Because it allows us to automatically isolate these cells. So we didn't have deep learning back in the day where you could actually just train and learn, and you had to do everything stepwise. So we would have to separate the IHC positive cells and the IHC negative cells and then perform like nuclei detection on that. So here is just some of the results based on the color separation. You can see these are the original immunohistochemistry images. We have ER, HER2, and I think PR as well. And it really allowed us to easily segment the foreground, the brown objects, as well as the background. And this is like a pre-processing step that allows for more efficient analysis of the individual nuclei. I would say for a good while, I worked on this on and off more than 6 months, but I was trying to come up with a standardized IHC scale, and I was getting a little bit close to it towards the end. So we have the digital scanner. We have the industry super excited. We're developing clinical tools. There seems to be a business case for them. But then we kind of took a step back and we were saying, is this really that straightforward? Can we easily deploy these? Can we easily build these? And so the first thing that we thought about was the actual pricing model. Like, how are we going to make money off the algorithms? And at that time, reimbursement had already started going down. So everybody had gauged that they're going to use the reimbursement. So already their business case was kind of falling apart because if you're not able to bill as much, then you can't charge as much. But I would say the bigger problem was probably this last point here is that digital pathology was actually not routinely being used. So we had two scanners. GE had two scanners in Canada and maybe one in Pittsburgh at UPMC. And, so who are we going to be selling the algorithms to? So there's digital pathology not being routinely used, and therefore there's really no use case for clinical algorithms. So in addition to that, there was technical limitations. It was difficult to process these whole slide images. They were more than 10 gigabytes in size, 60,000 by 60,000 sometimes. Additionally, the image formats were a disaster. Nothing was standardized. You needed one piece of software to open Aperio. You needed another to open Hamamatsu. So it wasn't easy to do development. And also there was limited tools available. Everything we were doing was designing from scratch. So I built all my own filters, my own classifiers, my own segmenters. But it takes time. So what did that end up being? Well, that ended up resulting in the whole kind of industry taking a big stop on developing clinical AI algorithms for pathology. And so what this led to is a rapid evolution in the digital pathology technology space. And the first place was the image management software, where there was a really rapid evolution. And this led to web-based viewers and cloud-based storage. And this is a huge bonus, or I would say benefit, compared to radiology imaging, in that radiology imaging, you have to have your viewer installed on your desktop. I mean, they're starting to be able to do remote consults, but it's very clunky, very heavy. This is contrast to some of the new IMS systems that are completely web-based. I can send my pathologist colleagues web links for them to look at results. And so it's definitely more efficient. And also, because pathology images are so large, having them in the cloud allows you to access them by a link, and you don't have to move that big data around. So other things were popping up, like annotation features. Now there's rich annotation features. And talked a little bit about Sedin Viewer. That viewer is used worldwide as one of the, and it has a huge annotation suite. Image formats started to get more standardized. Like now we have the SVS format that is kind of universal. And we were starting to use these web viewers now for remote consults. So we're getting going. Then we had a big kind of push forward in the AI ML space. So deep learning really came to fruition during this time, about a decade ago, maybe 8 years ago. So we were getting access to convolutional neural nets, which were really good at image recognition tasks. Computational resources were improving. So like the students in my lab, each of them now have their own GPU computer to do deep learning, so they can do it on their own PC. And we were also starting to digitize a lot more. So hospitals were digitizing their clinical data, and we were starting to get access to bigger data sets. So we now have better algorithms, better computers, and larger data. Then this was also coupled with open source software that was made available. For example, OpenSlide is a really big one because this allows you to view the multi-resolution pyramid of whole slides, and it lets you read them in, view overlays. And so that was a really big step forward that enabled algorithm developers to start doing R&D. Typically, we do patch the images into smaller patches, but we couldn't. You have to be able to have code that can do that. So OpenSlide was one of the first ones that enabled that for us. And then PyTorch and TensorFlow, which are extensive deep learning libraries that are now repurposed and shared. So a lot of times we can share our algorithms with our colleagues, and it kind of accelerates innovation. Then there were some research algorithms being used, and it was being mainly used by pharma R&D companies, CROs. There's some reference labs in the US that I know do kind of like a CLIA certification and or research use only. They use algorithms. The big reference labs. I find that the CROs and the big reference labs are more readily adopting digital pathology and algorithms. Maybe they have more of a motivation to kind of speed things up. And then we were finally got to the point where the FDA approved digital pathology scanners for digital sign out. So that means that in 2017, finally pathologists can use digital pathology for routine sign out. Until this point, it was only approved for research use only. And at the same time, we had DICOM come to fruition, which is actually an imaging standard that will allow us to use both radiology and pathology in the hospital. Okay, so we made it to a certain point. There was rapid tech evolution, and I was fortunate enough to come back to academia, as it's always been my dream to be a professor and to do innovative work in academia. And so I will talk to you a little bit about what we've been doing. We basically focus on building apps to improve cancer diagnosis and management, and we do this through workflow augmentation tools. So we build tools that can score, grade, stage, and help with diagnosis. And I'll walk you through some of that work. So I've been working in K67 since my industrial days. I have built traditional image processing tools for that, but more recently we were one of the first teams to release a deep learning tool for K67. And what it does is it automatically detects the K67 positive and the hematoxylin and the negative cells automatically, and it provides automatic proliferation index. And so what we've done is we've applied it on the patch level, TMA level, as well as whole slide level, and we applied it on one of the most diverse data sets in the literature. And what we found was that it worked quite well, and it worked well across patches. So these are some of the original patches. These are some of the results. The green dots are the hematoxylin or the Ki67 negative cells, and the red dots are the positive. And this allows us to automatically, very quickly and efficiently count the number of cells. These were on the TMAs, and this was on whole slide images, and we were able to show that we had pretty good correlation to the whole slide images, despite not knowing the hotspots that were used to score the whole slide. While it was working well and on diverse data, we noticed a shortcoming of the tool in that in very clustered regions with lots of hematoxylin or negative cells, that it would miss, our tool would miss some of the negative cells. So we sought out to improve this by creating something called UVNet. We wanted to preserve the dense features in earlier layers, so we created this V-block, which basically helps for those dense feature preservation. And what we can see from the results, this is a tissue microarray. This is our original PyNet. This is our the modified UVNet. You can see on the zoomed in region that some of the negative cells were missed here, whereas they were detected in this result. And our metrics, we looked at nuclei detection. You can see here for both Ki67 negative and positive, they were plus. It was performing better visually and according to the metrics. We've also focused on improving out robustness to target data. So let's say we want to go and apply this at Mount Sinai now. We want to make sure that it's robust at Mount Sinai. So we came up with this method that allows us to, in a completely unsupervised automatic method, generate some noisy ground truth at the target site. And we use that to kind of train a model, and we fine tune with the good annotations. And what you can see here is that in the original model, it achieved 0.62 in the target site, but in the improved model, 0.76, and that was statistically different. So, and that's quite a margin, actually. When you do these metrics, usually you look for like 0.01, 0.05 increase, but this one was significantly better. So using our robust Ki67 tools, we took part in a study with one of my pathologist collaborators, Susan Doan. And what we did was they supplied us with 500 TMAs, and we were blinded to the ground truth. And we ran our algorithms on it, and we gave back our proliferation index estimate. And they took our results as well as two commercial solutions, so a Perio Definiens and an open source one, QPath. And what we found was that ours was more reliable, had less error, and it also had higher agreement. So we beat the industry competitors, which was very satisfying for us as an engineering lab. And actually, this paper was recently awarded one of the best US CAP papers for 2024. So that was a pretty big honor as well. We also have been focusing on grading. So I've been working on nuclei segmentation. We're actually a big segmentation lab overall. In 2021, we published this in Middle. It was a dual stream gated CNN that has the regular stream that performs the nuclei segmentation, and then this edge stream that tries to predict the edges to kind of try and separate overlapping nuclei better. And I'll just bring your attention to these two graphs. You can see here, these nuclei were clearly separated, whereas in this one, it wasn't as clear. So adding the edge stream definitely helped. We also looked into, whether we need to use color normalization before segmentation of nuclei. A lot of works will either apply it or not, and we wanted to really kind of take a deep dive. And that's because what we were noticing is that, I won't get into this too much, but basically we built a model on unnormalized images and on color normalized images, and we compared the results, and we found that in images that have poor contrast, they improve the performance the most. So what we kind of started to think about is that, if the contrast is improved using your color normalization method, then your nuclei segmentation is improved. So this is an example here, really poor contrast, original segmentation is poor. This white means that a lot of them are missed. But once we've applied the color normalization, you can see that we've detected more of the nuclei. But in this one, you can see that the actual contrast seems to be decreased, and in that case, it worsens performance. So you have to be careful what pre-processing steps you apply. We're also working on creating a kind of multitask nucleus segmentation method. We've recently submitted this work to IEEE JBHI, and we found that the proposed method was outperforming the related works, and we've also started to integrate it into a pathology viewer. We've worked on mitosis segmentation and detection for a number of years. Actually, I've worked on this since I was in industry. I personally worked on mitosis detection. It's a very challenging task for automation. It's just due to the multiple phases of the mitoses, as well as just their general variability of their appearance. So we designed this conditional GAN, or generative adversarial network. And so you have a generator that produces the estimated predictions, and then we had a discriminator. And what it did is to try and determine whether this output mask was realistic or not. And this was extremely interesting because without this, it actually didn't perform as well. So this this discriminator helped to improve performance and reduce the false positives. We also further enhanced this work and submitted it to the MyDog 2022 challenge, and we built a Cascade RCNN, and we won 7th place in that competition. More recently, we've published this work. This work was based on lymph node metastasis segmentation and to predict the grade. And so in this one, what we did was a lot of the works, what they would do is they would get a rough segmentation of the patches, and then they would train a classifier to predict the lymph node, the stage. Sorry, not the stage. I guess the score, like whether it's ITC, micro.
The extent of the invasion or metastases.
Exactly.
Yeah.
And so what we wanted to do is just do it based off raw segmentation, measure the largest diameter, and see how well we could predict. And actually, we got pretty decent results. And this is on a held out data set from St. Mike's Hospital. We partnered with Kieran Jacati there, breast pathologist. And one of the interesting findings from this work was that ITCs is a massive problem. And while, according to the latest guidelines, ITCs are not being reported, I believe, for breast, and which maybe is a good thing for algorithms, because if we have to detect them, it's a problem. And sometimes ITC can be the size of your patch. So if you miss one patch, you've missed ITCs completely. So what we did here is we basically curated our data set in a very kind of robust manner, and we were able to get this was the best performing models out of everything that we compared. So positive would be micro and macro, and negative was ITC and negative. So yeah. We've also worked on some diagnosis work, so like computer-aided diagnosis. This was with renal pathology with Dr. Rohan Zhang, renal pathologist at UHN. This was an interesting project because renal pathology actually has the least acceptance of AI, or renal or nephrology in general. So we actually, when we first started to work in this and we wanted to publish, we found a paper that showed all the other fields, and nephrology was the very last. So the way that we started working on this was using explainable features first. And we looked at glomeruli diseases like minimum change disease, membranous nephropathy. We looked at the kind of membranous diseases, and we wanted to see if we could automatically diagnose them. And the reason why we were doing this is because the measurements to get these disease labels are done on an electron microscope. And so Rohan, he does that, and he does that for a lot of different centers at UHN. But if you go to like other areas of the world, or even within Ontario, they might not have access to that same technology. So what we were thinking is, could we provide a kind of a secondary read of these, if you will, or like a triage tool, like, yeah, we think it could be like membranous nephropathy or thin basement membrane disease, and perhaps either then sent it for confirmation, or just to provide the information that we got from the images. But the key point here is we wanted it to be really explainable. So we first did the glomeruli segmentation. Then we did biomarker feature extraction. So we looked at color, we look at morphological features like shape, distance between cells, size, and then we also looked at texture. And then based on those features, we built classifiers for the whole slide level. And you can see here, using a configuration, we got around 67%. Rohan really loved this tool because we did we kind of did a post hoc analysis after that. We went back and we wanted to say, okay, you know what? The most important feature for this classification was the texture. How come? And he was able to kind of correlate it to what he would be expecting to see in the pathology specimen. So then we did the explainable piece and kind of broke into the nephrology space and published an AI paper. We're one of the first ones, I would say. And so then we jumped to deep learning, which is more of a black box scenario. And, interestingly enough, we got pretty comparable performance to our kind of handcrafted design. And that's probably largely due to the sample size. But we did use a pre-trained network. So it was kind of as good as it could get. And we really wanted to try and still provide that explainability. So we used something called a GradCam map, which tries to show where in the image was important for making the decision. And you can see that it's usually in the center of the glomerulus. We've also been looking at foundation models for diagnosis. They're all the rage. There's a lot of them out there. This is a recent work we've been looking at in here, and it's been submitted to IEEE TMI. So now we have a bunch of tools that we've developed, validated, even did prospective testing. So now how can we start to get people, and pathologists in particular, using our tools? So we created this deployment pipeline, which is with our one of our collaborating partners, PathCore, and it basically gives us access to an API that lets us make our own code, but push our images and our results to the cloud for display. So we can automatically automatically train and we can automatically test as well. And so this is an example of our Ki-67 algorithm integrated into PathCore Flow. You can see here the yellow dots are the Ki-67 positive cells and the blue dots are the negative. So now that we have this robust tool integrated, we wanted to do an international digital pathology study. And what we did is we were fortunate to have a good network to get a lot of around 90 pathologists to respond to our survey. And what we wanted to do was to compare the pathologist Ki-67 scoring accuracy, concordance, and turnaround time with and without AI assistance. So this is what they would see. They would see first the image without the aid, and then we would do some time later with the aid. And the information that they were supplied is the overlay of what we detected. And in the survey, they were given the PI, the recommended PI from the AI. And what we found is that pathologists were more accurate across the board over all 10 TMAs using the AI. So this is PI error. So a lower error is better. And you can see the red is the with the AI, the blue is without the AI. So there's more error. And also there's wider variability without the AI tool. And you can see this by just looking at the means, right? So the mean error is less compared to without the aid. What was interesting too is that this trend was consistent based on the years of experience as well as the career stage of the pathologists. What we found with in terms of agreement was something kind of that really personally excited me as just somebody who's always thought about how these tools can impact patient care. And so without the AI, so on the y-axis, this is the without the aid, and this is the ground truth proliferation index. And you can see that there's a bias, that it's overestimated at low PI and underestimated by the pathologist at high PI. So what does this mean? That means that depending on the pathologist reading the case, if it's used to assign therapy, patients may or may not receive the therapy correctly. But with the AI, you can see that that's tightened right up. So what this means is that patients will receive the same treatment for the same disease, independent of the pathologist reading the case. And so we just published this actually at the AACR meeting, and I'll just bring your attention to this. So Ki-67 for breast, there usually used to be a 20% cutoff to decide therapy. And so without the AI, 66% of the pathologists got that correct, whether it was high risk or low risk. But with the AI, it was 97% correct. That means that 97% of the patients are going to receive the correct therapy decision. And that allows us to standardize our measurements across pathologists and labs and centers. This is turnaround time. It shows that it's a little bit faster. We also looked at, whether there was trust. And it was funny because some of the pathologists actually would say, so we defined a measure to measure whether the pathologists were accepting the AI recommendation. But it was funny because we found end of survey questions. Some of the pathologists were like, we don't want, it's not ready. It's not time, but they are the ones that accepted the recommendation. So this was a lesson to my students and my lab in general that we're building tools that they need to work because, if pathologists are trusting us and trusting our recommendations, they need to work, and we have to be transparent about how they work and where they fail, basically. So I have just about 2 more minutes left here. I'll just quickly kind of whip through this part. It's just like, okay, so it works, it helps. So where are we now? Well, there's only one clinically approved FDA algorithm. Actually, I think there's 2 now. It hasn't been updated yet. So how come, it's been so slow? Well, there's a lot of considerations for translation. Anne really talked about it nicely. nicely is about understanding the pain point of pathologists. Sometimes you'll get research labs going and creating their own algorithms and try to fit the use case to what they created. It doesn't get adopted like that. I did talk a lot about these at previous conferences, but there is a lot of things that we still have to think about. There's also, pathology from an R&D perspective, it's a relatively new field. So like you look at radiology imaging, the number of publications in AI has been going for a number of years, whereas you see for pathology, it's just new. And this comes back to what I talked about earlier in my presentation about how scanners are just starting to be distributed and used by hospitals. So we need to pick that up because, without a significant innovation space, companies also will be slow to innovate. Um, one of the reasons why it's tricky to actually implement digital pathology is because the kind of return on investment seems to not really be there, or it can be had after 5 years. So this study basically said that, you need 5 million euros to equip your hospital with digital pathology, and in 5 years you will make that money back by savings in time, etc. This is one of the first studies that has actually showed something so clear and concise, to be quite honest. And so that brings us to now we're implementing it, now the value of AI to digital pathology is becoming more clear. It was initially thought that the first frontier for medical AI is the pathology lab. That's because the images are complex, there's a lot of counting tasks, but there's also increasing pressure on pathologists. So what this shows is that, the number of active pathologists in the US is going down, but there's increasing caseloads. So there's more pressure on pathologists to do more work in the same amount of time. So industry thinks that provides for a supportive business model for adopting AI and digital pathology. But then I found this study which shows that, it says artificial intelligence and radiologist burnout. It's not for pathologists, but I really had to go in and look at seeing why. Why are people who are using artificial intelligence more burnt out? And basically, it was because I had to go and look it up, is that they were doing more cases and more work hours per day in the AI group. So, the big focus on making radiologists and pathologists more productive to alleviate their workload pressures might actually have the opposite effect. So that's why we need to do this as a multidisciplinary team, work together, understand the pressures, and work together. So in the future, I really still believe that we're going to get these workflow augmenters. We're going to start complementing this information with multimodal models for companion diagnostics, precision medicine, and integrated diagnostics. And so, while it's been a long journey, I'm still hopeful that we will get there. And so these are some pictures of my team. I just like to bring attention to the fact of how many ladies I have in my team. This is a very new, I'm not sure how it is in pathology, but in engineering, there's not a lot of women. And so I would say that this is the first time in my life that I have more females in my lab than men. So lots of love to the guys, but also a big shout out to the ladies of the lab. So thank you to my funders and my students and my collaborators for making this work possible. Happy to take any questions.
Thank you, April. I think that's both yours and Annie's work is really impressive. I want to congratulate your all the accomplishments, and I want to specifically appreciate your understanding of pathologist needs, and you have very like pathologist-centered mindset, which is I think is very important. So we do have several questions in the chat. It's interesting. KI67 comp tools is actually one of the earliest AI algorithms that I knew when I was a trainee in pathology. That was, about 10 years ago, I think people start to use that. And I would, at that time, I would imagine, that's the trend of how AI further research will go. Because I think not only we have more caseload because of populations, but
Hmm.
also our complexity of pathologist work getting more intense, right? Like the level of information and amount of quantifications and grading that's required by pathologists has been more demanding over the years. And you would imagine that more tools like KS67 count or IHC quantification tools, especially for hematopathologists. Like we have two hematopathologists from Toronto asking, why, how can we have tools that help us quantify specific IHC markers like CD34 or CD138 versus
Hmm.
MOM1. But interestingly, I think most of the FDA or UKCA approved AI products in pathology are from breast. And
Hmm.
both of you are like, well, your works are mainly focused on breast. It seems that our breast colleagues have a head start against, other subspecialties. And I wonder why is that, what is the incentive, like driving where AI and pathology are going, where the manpowers are mostly centered in.
Anne can talk for how she did it, but basically, when I started working in industry, they they asked me to look at the most prevalent cancers, and there was prostate and there was breast cancer, and my mom was a breast cancer survivor, and that's how I thought I would get into that. And I worked on mammography for my master's, and so I understood a little bit about breast cancer. Um, but it is a cause kind of near to my heart. So
Any
yeah.
any comments?
For me, it was again just the environment. So I came from the UK working in stroke and MRI, and then when I came to Toronto, the MRI equivalent was in breast. Don Pluis was doing. We were the first in Sunnybrook to do MRI screening, so I had involvement with that. And then Martin Yaffe was the one who introduced digital pathology to Sunnybrook, and he's a mammography person. So again, it's more that was the environment that happened to be active, but more and more now we're moving outside it. So April was talking about kidney. I've done some work with hepatopathologists. I'm also starting to do some work with colorectal cancer, hopefully. And we've done some collaboration with the colorectal pathologists at Sunnybrook and and moving into prostate and things like that. So as you go along, it's more a question for me is who are the keen collaborators and who are the collaborators who have the time and the energy to come up with the problems and things like that, because unless they're pulling, there's no point in me pushing. So that's one of the
Yeah,
motivations.
and
Sure.
I think you, Annie, raised a very good point at the one of the our tasks. Well, one of the roles of pathologist is actually to define the task, right? And I personally, I'm a head and neck pathologist and bone soft tissue pathologist. I think there are a lot of interesting questions I have, and I'm really motivated to collaborate on different fields. And judging by the but people around me and also questions from the chat, it seems pathologists are eager to reach out to you, especially for pathologists who don't have access on-site scanners. They want to, they have questions generated from their daily work, but they don't seems to know how to, build up the collaboration and form a network. And that I think that leads to important questions. Both of you came from industry, and actually both of yours early work were in radiology, and now you're more devoted in pathology related or digital pathology related AIs. What do you think are the biggest hurdles for translation or deployment of these research results into like commercial products or the products that we can use? And I would like to probably ask you to comment on, or your vision for the University of Toronto community or the Greater Toronto area, and how pathologists can work more closely with you on, about engineers and AI scientists to work together, both in this, research field and also clinical.
Do you want to go first, April? You've got more commercial experience than I did. I didn't actually come from industry. My only industry thing has grown out of my lab and not vice versa. So April is definitely the industrial person here.
Yeah, I think, well, hopefully it was appreciated by kind of how, I told the story at the beginning. Like, we had jumped ahead, we were designing these algorithms, we were thinking about computer-aided diagnostics, and then we didn't even have a clinically approved scanner. So there has been like a couple of bungles like this, I would say, is like, so it's hurt the adoption and the acceleration of the tools. And so I think the way that industry is going is that they'd like to focus on the low-hanging fruit and things that they know will make money. So, this is why, like, for example, I told you that when I was at GE, they asked me, would you want to work on breast or prostate? And that's basically because those are the most amount of cases. So the most amount of people to treat, which, that's actually one of the reasons I left industry, is I felt that's not super noble. We're, putting numbers on people, right? So I think the way that it's going is, for example, like some of these quantification tools. Yeah, like I'll give another example of how the industry is rushed. So these foundation models, I mean, they do an okay job, but the industry, even companies now, have gotten like 1 million slides, partnered with Microsoft, cut them up into billions of patches, and created these foundation models because they thought that there would be a need. But we don't really know if it's going to solve the need that we need yet. And what is that? So I think we're going to, because the idea is to come up with one model that can handle a lot of things, right? But I've been working in this space for a long time, and I'm skeptical on that.
Yeah, I saw Annie was shaking her head as well.
Yeah. Like, I think everybody's hoping that you're going to get this magic button, and it's going to be one model, and it's going to do lymph node metastasis. It's going to do, nuclear grading. Personally, if you want your tool to work well and be a good one, you want to make it application oriented, your tool. So, it's a little bit daunting in the sense that if you think about, even personally, you, Lingxin, of all the grading and the different steps you have to do for, let's say, one type of tumor, you would need different tools for each one of those steps, right? So,
Yeah. Well, like Annie would, I think, your work is mainly centered in Sunnybrook, and April has done a lot of work with UHN and St. Michael's, but are you kind of more incented to validate your algorithms? You have talked about at different centers, and I feel like a U of T community, we have a little bit different focus, but there's a lot of common overlap. We have some shared needs as well. So Annie, what do you think we can do?
I mean, I was just thinking, as April was talking about the Ki-67, I'm thinking, well, I've got a lymph node that works quite well. Maybe what we should do is get together and say, right, okay, I'll test your Ki-67 on our data if you test our lymph node metastases thing on your data, and we'll all get together and do it that way. So I mean, the problem is that April and I are both kind of, we're competitors in some respect, and that we're both going to the grant application. The only way we can fund things through our lab is basically through grant review funding. Okay, and you get your grant review funding by saying we're better than everybody else, we can do this, and nobody else is doing this, is unique, which of course is not really the same thing as translation. So what we do need to have is a better way of looking at models thing. But industry is important because the only way you can ever make a clinical impact is by having a product. So we're not allowed to say give our algorithms away to another hospital may not be allowed to use it. So one thing we could do maybe in Toronto is have some sort of system where we can have an easier way that we can test algorithms in a kind of clinical environment between the different healthcare systems. So I don't think Trinity, I know April, you're kind of assigned to Trinity is it Trinity? No, what's the health?
Unity.
I always get Trillium and Unity mixed up to go to Trinity.
But I
Anyway,
think Trillion is part of Unity, yeah.
Yeah. So anyway, we can kind of get some kind of overarching approval process where a developed lab algorithm from April, for example, can be tried out in a clinical context at Sunnybrook and so on and so forth. I mean, we still need to figure out how to put these things into the clinical workflow. So at the moment, for example, at Sunnybrook, we've been completely digital since about August, but we still don't know how to orchestrate this stuff. So we still don't know how to get the correct images out, put them through an inference engine and put them back to the pathologist. Even if we'd got all the approvals and stuff, we still don't have that smooth pipeline. The clinical image management systems, the ones that the pathologists are using, they have hooks to some of the companies because they've been working together, but they don't have hooks for generic research algorithms. We both use Flow because both attached to it, and it has an API, but that's for research use only. So what we need is a way of pushing our results back to the clinical workflow as well, and so on. I went to a very interesting, so back to your thing, April, about the multiple models. I totally agree with you that one model is not going to be efficient to do everything. And you can train models that are multitask, but they tend to be bigger. I know there's some work in radiology on making this efficient, so eventually we'll get better. But another approach to it is that you're always going to have lots of different models. I went to a meeting on Monday down in Montreal from PAX AI. So this is the radiology field, which is much further ahead than pathology. They have DICOM databases that are more standardized, but what they're doing there is the group there is looking at agentic AI. So the idea is that you have, say, 20 different models sitting in the background ready to go. So you might have a Ki-67 module, you might have a P53 quantification, you might have a lymph node quantification, you might have a cellularity. And what they're working to doing, which is an interesting idea, is at the front end, it can you push a button and it will find which images are correct, check the right images, send it to the algorithm, get the algorithm results back again. But then on top of it, you've got another agentic AI. So the clinician types in a question like, I want to assess cardiac function or something. And then the AI will say, okay, to assess cardiac function, you've got these images. We have this model, this model, this model that are all relevant for this. Let's go push the data to that. Or say somebody has some pathology data on this. So say I've got a breast case post-neoadjuvant therapy. I say, I want to know residual cancer burden. It says, okay, we've got 4 different models here. Let's go fire them up, or Ki-67 or whatever. So the idea is rather than the pathologist having to know exactly every time, have to think, oh, I've got to do A, B, C, and then I've got to integrate the results or something. You have some kind of orchestration agent that figures out what needs to be done and put it in again. So I think that's the far future. I think that's what would be lovely to go to. And as we build more and more algorithms, that's going to be more and more sensible. And then back to the collaboration, I definitely think we need to figure that out. There was another webinar some time ago that had, I think it was David Huang, gosh, I can remember surnames, but UHN, and also Andy Evans. And Andy Evans' take on can we use research algorithms in the clinic was, well, as long as nobody's charging for it, and it's just for information and not for diagnosis, then we should be able to do that. It should be possible to get that done. So I would love to see a consortium where we kind of have the thing to do. Yeah, you need resources though. Every time you build a new model, my students has to run it.
Those are great comments, Annie. I'm not sure if you are referring to the CAP-ACP meetings that happened in Montreal at the beginning of this month. But like we're actually hoping
a separate meeting. It was radiology.
It was a separate, the radiologist meeting. So what you have pictured the radiologist doing, it actually makes more sense. So I would always like to imagine that the future AI will function as a kind of senior resident or more experienced assistant. Uh, the problem is, like we currently judge a AI algorithm by uh, the maybe it's very good if you have a 95% of probability or predictive value, but that's not really good enough for pathologists if we just entirely trusted the algorithm to do the work and give us a number without supervision. The main reason is if I have a fellow through training, there are different checkpoints and parameters that I can teach them, and I know exactly I can teach them to have the same logic, same like way of thinking, the same guidelines that we can follow, and I would know exactly where he or she went wrong. With AI, with a black box, that's a different story. So I wouldn't necessarily know, like AI versus, several AIs even that may spit up different results. And I couldn't interfere with the middle steps to alter them and to, like make them think like a pathologist. So it makes more sense if we have a selection of different tools specifically for tasks down the road, as according to our needs. And I always question what is the foundation models mean. Does it mean that instead of the current detection, quantification, grading tools or a binary tool, does it mean that it's an almighty kind of pathologist like model? It's hard to imagine that because even uh, you know pathologists, we can't be good at all the subspecialties. We have to, in order to catch up with the delayed updates, we have to be more focused in one or two subspecialties now. So it's really hard to imagine a foundation model can manage to do like what a general pathologist can manage. And that's also the question, one of our audiences said, is AI going to be autonomous? So right now there's some weekly supervised or unsupervised model in the training. Do you see that as a future, or a direction of the AI development?
I think the training of the AI models will become much more autonomous. So we can't carry on with the situation where we ask our pathology fellows to spend weeks and weeks and weeks annotating. It's just not scalable. And we do have technologies that can do weak annotations and things. But at the end of the day, to get the really high level of accuracy, you need someone to then fine tune it and manually correct it and things like that. So yeah, I think the autonomous stuff can help to bootstrap, so we can give almost everything, but the last kind of, it's like the chef in a restaurant, isn't it? In a top restaurant, the chef doesn't cook the food, but they put the little last piece on or do the quality control check and things like that. That's how I see AI working in a pathology lab. The pathologist becomes the head chef who checks at the pass that everything is in order and correct and works.
And also, like, it seems that, similar to radiology, pathology-based AI is, the ultimate basis or foundation is the patch or segmentation-based algorithms. So, like, like you divide pathology images into pixels, and you kind of convert a pathology questions into a mathematical question and go from there. But in reality, sometimes we don't need to know, like maybe on a slide, only 50% of the slide's areas is what we're interested in or informative. Like this scanning the whole slide, some institutions insist on scanning all the pathology slides at 40x. That creates a huge image that create, like generous increased cost for storage. Is there maybe a future strategy to, save on a storage memory by being smarter in selecting the areas, maybe, having kind of imitating the work habit of pathologists starting at the low power and less resolution, and then only dive in and zoom into high resolution in the areas that's most important.
I've always argued against that, because if you think about back to the lymph node metastases thing, as April said, if your MET is in one patch and you miss it, you've not got it. So if you try and go down at low resolution on that task, you're
Mhm.
never going to find that micromet. And in actual fact, the advantage of the AI paradigm is that it can scan every single patch quite efficiently. So there's no need to think that you have to work like a pathologist because it's a machine, it can go through everything. People have tried to do, I think Google at one point had a prototype where they had a robot attached to an AI algorithm that tried to control where it zoomed in and out and things like that. But at the end of the day, again, it's high throughput screen scanning. So, I mean, I don't think we're doing 40 times it's anything. I think it's 20 times, but maybe what you can do is high throughput, and then maybe then the AI can add the extra stuff. So, okay, this one you have to go to 40, this one you have to get an IHC stain. But I don't see it downgrading the existing standard of care, because the liability on that would be huge if you missed something.
That's a good point. April, any comments?
Yeah, that's actually uh, like uh, like a few years ago, before there was any FDA approved algorithms. I was trying to look at liability. Like, so, and one of the things about the considerations of pathology, translation, how come we're not there yet in that talk? I looked at different frameworks for liability. And pretty much, if the pathologist uses the tool to come up with the diagnosis, or but it's the pathologist that made the decision, then I guess it's like the pathologist has used another tool in the lab, and they're the ones who are ultimately still liable. It's when you have a complete autonomous AI, then the companies are liable. And so, like, for example, like a triage tool, like looking at lymph node mets, maybe most of them are negative. So, what the companies were initially looking at was like, okay, can we triage this data so that you only look at the positive ones and the negative ones we throw away? Not throw away, but we archive them basically. Or they can, the pathologist puts it as a as a low priority, and the pathologist can look at it later. The problem with this is that the AI is making the decision, and it's so. I think companies don't like that, quite frankly. They've been steering away from that because they don't want to be the ones that are liable. So actually, maybe not in lymph node mets is a good example, but breast mammography. So in that case, there's only some that are very few compared to the screening programs that are positive. So what companies wanted to do was going to say, okay, we're going to give you the top 20% ones that we determine look risky, and you don't have to screen the other ones because we're pretty sure it's negative. So companies were loving that because they could basically have a great business case for that. Like, instead of reading 1 million, you're going to read 20,000. And that it's quantifiable what savings are had. But I think because of the liability piece, they're moving away from that.
Right.
And so, yeah, is that around the question that you were asking there?
It is definitely related. I think
Hmm.
could it be the um same reason, like the liability issues, or was it more of a cost related issues that it seems that in the Greater Toronto areas we haven't really adopted any of the FDA approved commercially available algorithms to my best knowledge. Rather, I think most of the centers, including UHN, Sunnybrook and Unity, and hopefully
I
Mount
don't think
Sinai to
so.
follow are developing our own algorithms? Or is it
Hmm.
because, you believe homegrown algorithms are better validated for the specific patient population or the environment?
There's definitely some of that, like AI fairness and bias that you have to consider, whether your algorithms work equally. This is why doing research in Toronto is great, because I think it's 30 to 40% different ethnicities compared to just white men and women. So, validating in Toronto is very good as well, but using the data to train is also good from that perspective. But I haven't really heard of any tools being clinically used. I mean, I did meet some pathologists that were part of a reference lab, and it seemed that they were using some, but they weren't very clear about what they were using. So I think there's a lymph node, there's a prostate. I think Andy Evans has actually been using the prostate Gleason grading tool. So, and that one is yeah.
Someone asked online, and if I had to, certainly Sunnybrook aren't, but if I had to guess that anybody was, maybe he was. In fact, he might be Phillips. But I don't know if anyone knows how much these things cost, but I imagine they are quite expensive.
Yeah, that's a good question. I have no idea. It probably depends on the number of users.
Different business case.
One seat, one license, or more than one.
There definitely a lot of administrative and privacy related concerns and questions that haven't been resolved amongst the hospitals. I think personally I have worked with Dr. Andy Evans on the building of a digital pathology network Ontario, so with the hope that we can share consult cases. But like obviously ultimately each individual hospitals are the guardians of the data. And to date, it's maybe a gray area how we can share this data and cross-validate the algorithms. And certainly, it will continue to be a most interested topic in this community of interest. We will explore ways to find ways to remove these hurdles, and so that we can be more productive. So, with that, I want to thank you again, Dr. Anna Mattal and Dr. April Khademi, for taking time and sharing with us your phenomenal work. This is actually the second seminar of our series event. You can access the recording of the previous session presented by Dr. Phidias Diamandis and Dr. Yarnis Presses through the CPD website. And I think in the chat, Jenny just shared the link to that website in case you want to save that. Please remember to complete your evaluation for your CME credits. And we are actually going to hopefully invite Dr. George Yosef to have an update on the 2025 CAP-ACP Digital Pathology and Precision Diagnostics Summit. And Dr. Yosef is the LNP lead in the strategic plan for digital pathology, and we would like to discuss some of them, questions related to management and policies around U of T and the greater Toronto areas, and how we can further promote digital pathology. Okay, and we have actually 5 more minutes. Any questions from the audience or any comments?
There's a few questions on education in the thing, so I don't know whether there's a good set of resources from any of the colleges. I know there's lots of recorded talks, so you can go to any number of research talks and things like that, but I don't know if anyone's actually organized any systematic kind of course for digital pathology.
Yeah.
Can chime in?
Yeah.
Hello. I did attend the Digital Pathology Summit, so I can kind of give a sneak preview. I think, at the national level, like the CAP-ACP is going to plan to have like an education committee specifically on AI education. So for the people who ask that question, like stay tuned. Maybe Dr. Yusuf will elaborate more on the next meeting. But probably, you're gonna get anyway at the next committee of interest, he probably will elaborate more. And then I just want to comment on, I think we're talking about why like places like Sunnybrook and we're using digital pathology, but we are not using any of the AI algorithm. I think really the main, I don't know, at least for Sunnybrook, the main thing is the cost. In Canada, there's no really reimbursement. And like April was mentioning, like in the US, like there was reimbursement, but then cut, and then I'm not even sure it's still reimbursed or and so like and in Canada it just never has reimbursement period. So I think the cost is the main issue for using the commercial one. They are very expensive. Like you kind of, my understanding is like it's like per case or even per slide, and
Mhm.
the cost is all over the place because it's even the company they themselves, they don't really know how to price it. Kind of, because there's no reimbursement model. So that's why
Mhm.
the APACP, hopefully they will also be working on it, kind of have tried to develop a building code for AI algorithm and digital pathology. That is sort of something that like, well, at least at the summit they were discussing it. But so I think yeah, because I think yeah, so that's the
Yeah,
that is
this is a general good thing for pathologists to see competitions amongst different, like AI developers. But we hope, also hope that we can work closely to see like to bring a good solution.
Well,
I
it's
think there's still like a great increasing demand for pathologists uh, to these AI algorithms to help us.
Well, I really think that it's so nice to see so many pathologists on this call having interest in AI and pathology. We can't do it without all of you. This is to build technology to help the pathologist. I always say to help for the pathologist, no, with the pathologist for the pathologist, because if we're going to try and fit technology to what you do, it's never going to be adopted. It has to be a partnership. And, I remember when I first started in this space and digital pathology was just taking off, it seemed, people were interested. I was giving talks at a CAP, different places on the potential of, and it was image analysis for pathology. And I think because there wasn't a lot of digital use, it was such a bizarre idea back then. But to really see pathologists very interested in this, it's exciting and yeah, it's great to see.
Yeah, and I think a lot of pathologists in the audience are interested in knowing whether you have specifically any April, you have any opportunities of collaborations for your existing projects that needs help from pathologists. I think if you have any information, you're welcome to share with me or the CPD office, and we can we'll possibly will post it on the website. And again, we
Sure.
hope to keep this community of interest like a long-term platform for pathologists and experts like you to get together and have discussions. And obviously, down the road, we'll invite policymakers and leaderships in this area to the discussion of our common questions. Okay, so
Sounds great.
yeah,
Yeah,
that's a
happy
really
to
nice
if
session. Yeah.
yeah, if anybody is interested in collaborating in any of the projects or similar works, please feel free to reach out to me.
Okay. Well,
Thank you so
have
much,
a nice
Lingxin.
afternoon. Good
Great to
afternoon
see
to
you,
everyone.
Anne.
Nice to see you too, April.
Yeah, we'll see everybody soon.